Good morning, everyone. My name is Jaeik Kim from the ADAS Lab at Seoul National University. Today, I'm excited to present the work Train for the Worst, Plan for the Best, Understanding Token Ordering in Masked Diffusion, which was recognized as an outstanding paper at ICML 2025. The stunningly realistic images and videos we see today, capable of producing incredibly high resolution results. However, the success in continuous domains has not yet been fully replicated in discrete domains such as text or protein generation. In today's presentation, I will focus on specific type of model designed for this challenge, the Masked Diffusion Models or MDM. Masked diffusion models are a leading and promising approach for discrete data. They have been explored in several recent high-impact papers. The core idea is to learn how to generate data by reversing a process of randomly masking or hiding parts of the input. These MDMs have recently begun to scale with notable examples such as LADA, DREAM, and JES2, aiming to push the limits of scales and improve performance. So how do they work? The training process or the forward process is straightforward. We start with a complete sequence like a sentence. Then we randomly select some tokens and replace them with a special mask token. This process is repeated, creating various masked versions of the original data. The model is then trained to predict the original tokens for the mask positions. To be more specific, the model's job is to look at a partially masked sequence and for each masked position. Then predict what the original token was. It learns to unmask or infilling the missing information. The generation process or inference works in reverse. We start with the sequence of all masked tokens. Then step by step, the model predicts tokens to infill in the masks in what we call vanilla inference, the order in which tokens are unmasked in random. This process continues until the entire sequence is generated, repeatedly remasking tokens at random along the way. Despite their promise, MDMs currently underperform compared to the more traditional autoregressive models or ARMs, especially in areas like language modeling. This leads the authors to two key questions. First, what are the fundamental strengths and weaknesses of MDMs compared to ARMs? And second, under what conditions can MDMs potentially challenge the dominance of ARMs? To answer these questions, we need to understand the central trade-off. On one hand, MDMs have a higher complexity at training time. They have to learn to predict tokens in any position given any random context, which is a much harder task than the simple left-to-right predictions of ARMs. On the other hand, this difficult training gives MDMs incredible flexibility at inference time. Unlike ARMs, which are locked into a fixed generation order, MDMs can theoretically decode tokens in any order we choose. This leads to the paper's central research question: how can we leverage the inference flexibility of MDMs to overcome their inherent training complexity? Before we examine the author's analysis and proposed solutions, let us first provide some preliminaries on masked diffusion models. As with other diffusion models, as an MDM begins with a forward process. To clarify the notation, we denote L as the sequence length, alpha t as the noise scheduling parameter, and EX0 as the one hot vector representing the ith token in the vocabulary space, and 0 as the ID of the mask token. Using this notation, let X0 be sample from P data and let T be a noise level sample uniformly. The forward process is then defined as follows. We denote this process by Q, which follows a categorical distribution. Upon examining the categorical distribution term, it is straightforward to see that each token is masked with probability 1 minus alpha, while the original token is preserved with probability alpha. Next, the reverse process also follows that of conventional discrete diffusion models. From the perspective of a continuous time diffusion model, if we take two continuous time steps S and T, the reverse process Q of X given T is defined as follows. In this case, when XTI is not a mask, the reverse process proceeds in a way that preserves the unmasked token. Conversely, if XT is a masked token, the reverse process applies a specifically derived formulation to unmask the token with a prescribed probability. Likewise, in MDMs, the reverse process is parameterized by a BERT-like denoising network, which is trained to approximate an elbow-based loss, thereby enabling optimization of the entire diffusion process. It is known that the elbow-based objective of such MDMs is equivalent to the objective of masked language modeling, or MLM. In this paper, the authors interpret MDM as an order agnostic training model. To support this interpretation, the authors introduced the following notation: X0M denotes the original sequence in which the tokens at the indices specified by the list M are masked. In proposition 2.1, the authors provide a reinterpretation of the MDM objective, demonstrating through a formal derivation that it can be viewed as a multitask model trained to optimize the MLM loss over multiple masking permutations. By closely examining the expectation term, one can see that it corresponds to the MLM objective. Observing the permutation term above, along with the fact that M is drawn from the index list L, we can interpret the MDM as a model that learns to handle all possible permutation masks over the entire sequence. As a result, we arrive at the conclusion that MDM loss is a linear combination of the losses for all possible infilling masks. In this paper, AR and MDM are interpreted from this perspective, and it is argued that autoregressive models, or ARMs, solve only a small subset of the mask infilling problem. As shown in the following equation, The AR objective can in fact be viewed as a diffusion objective that trains by unmasking tokens strictly from left to right. In doing so, it addresses only a very limited subset of the possible infilling problems among the vast number of masking permutations. By closely examining the following mask index list, you can see that it contains indices corresponding to masking the entire sequence that follows the token already revealed so far. For example, if we view AR from the narrow or infilling perspective of MDM, the forward process of AR can be understood as a progressively inserting masks from the right, one token at a time. In contrast, MDM solves a much larger set of permutations, namely the infilling problems corresponding to a wide range of masking index lists. Intuitively, this is more challenging task for the model than solving only a single infilling problem that proceeds strictly from left to right. To demonstrate MDM's train on hard problems, the authors define latents and observation distribution, or LNO distribution. LNO distribution defines a data distribution P data over sequence X. First, there is a permutation pi over the indices. The sequence is composed of n latent tokens combined with p observed tokens, forming a total L tokens. A prior distribution is defined over the latent values, and a learnable observation function is introduced to map these latents into observations. Within this distribution, latent tokens are drawn from the prior, and their positions in the sequence are specified by the permutation pi. The observation tokens are generated by applying the observation function to the corresponding latent tokens, and these observation tokens also have their positions determined by pi. Let us consider an example. Suppose m is equals to 5, meaning our vocabulary consists of 5 distinct tokens, and we have two latent tokens and one observation token. Assume the prior is a uniform distribution. We first sample 2 latent tokens from this uniform prior, and let this be 1 and 3. If we take our observation function to be simple addition, the resulting observation token x3 would be 4. Combining this, we obtain the sequence 1, 3, 4. Here we have assumed the identity permutation, so the tokens appear in their original order. In fact, ARMs use identity permutations for training in terms of LNO distribution. This is a relatively easy problem to solve, since the latent tokens can simply be drawn directly from the prior. Predicting the observation tokens is straightforward because once the latent tokens are given, the observation function, being a learnable function, automatically determines them. In general, for ARMs, the observation function can be regarded as a transformer-based language model that models the observation tokens. In fact, this assumes in AR that latent and observation tokens are generated from left to right. It should be noted that the notions of latent and observation tokens are fairly abstract. Put simply, the latent is closer to the cause, while the observation is closer to the effect. In my view, general text data tends to follow a left-to-right structure, whereas domains such as code or puzzles have a more shuffled or nonlinear structure. For example, let us consider generating the sentence "I love diffusion models" from the dataset. Now let us treat "I love diffusion" as the latent tokens. The observation token in this case would be models produced by feeding "I love diffusion" into the language model. However, this interpretation still comes with a limitation. While we may treat "I love diffusion" as the latent, in reality, we cannot be certain that it truly constitutes the latent representation. Now, returning to MDM from the perspective of solving token order agnostic problems, let us suppose that the observation function is a cryptographic hash function. In MDM training, there can be situations where, given the observation models, the model must infer the preceding mask tokens. However, in such an unmasking scenario, the model would need to recover the latent tokens by inverting the hash function, something that is impossible. This was in fact a worst case example. For a more realistic real-world scenario, let us consider the example of sparse predicate observation. This example, created by the others, is referred to as the LNO and ESAT dataset. Let us first look at the process of constructing this dataset. We begin by collecting n latent tokens. Next, using specific rule G, we construct a set of true-false OX questions based on these latent tokens. The objective of this task is to infer what the latent tokens were based on the answers to the quiz. For example, suppose we draw two latent tokens from the list AA and B. The resulting set of quiz questions would then consist of all possible combinations such as AA, AB, AA, and AB, as shown above. Based on these combinations, we apply a rule to determine whether the tokens are the same or different. This produces an answer key consisting of zeros and ones, which in our context serve as the observation tokens. The task of sparse predicate observation problem is to determine from the answer key, the observation tokens, which list of latent tokens was used to generate it. This problem is still inherently hard to solve. This is also similar to the well-known class of constraint satisfaction problems, or CSPs. In particular, it resembles the planted M coloring problem, where the task is to color each country on a map such that no two adjacent countries share the same color, using a total of M colors. In this analogy, the colors correspond to the observations, while the latent variables are the borders between countries. Similarly, given only the list of colors assigned to each country, reconstructing the original world map would be an extremely challenging problem. In addition, these CSPs can also be interpreted using a graph like the one shown here, where the x-axis represents the density of information and the y-axis represents the degree of alignment with the correct solution. The blue line corresponds to the setting in which hints about the answer are provided, while the orange line represents the case where no hints about the answer are available. Careful observation of the graph shows that depending on the amount of information, there are regions where the problem can or cannot be solved depending on the presence of hints. This indicates that although the problem is theoretically solvable, it remains difficult to solve with practical real-world algorithms. The authors empirically showed that MDMs are capable of solving more difficult problems than AR models. Before delving into the result, let us recall that both ARMs and MDMs can be viewed as a permutation pi learners. An ARM is a model that learns the identity permutation pi as shown below. And in MDM, in contrast, is a learner that solves all possible problems arising from arbitrary permutations as illustrated below. Experimentally, when comparing the negative log likelihoods of learners over permutations during training, they align according to flops. As shown in the graph, learners for easier permutations such as AR, which covers only a small subset of permutations, achieve lower loss during language modeling, whereas MDM or models trained on uniform permutation exhibit higher loss. Similarly, models that learn permutations close to AR fall in between these extremes, indicating that the degree of randomness in the permutation directly determines the difficulty of model training. Meanwhile, MDMs are not significant worse, even though MDMs are trained on exponentially more masking problems. The authors suggest that this may be because MDM is trained in a MTL-like fashion, solving a diverse set of permutation problems. They argued that when learning multiple tasks, MTL often fosters an emergent understanding of a certain underlying rules, which may explain why the loss is not as high as one might expect. Even after training, the errors of MDM remain imbalanced across different masking problems. At inference time, when we guided the unmasking process for text problems according to the permutation shown below, we found that the validation loss was lowest for the identity permutation. In contrast, when using uniform permutations, the loss was noticeably higher, at least for the text modality. Similarly, in the previous discussed LNONA SAT task, predicting the earlier latent token is more difficult than predicting the later observation tokens. As a result, during inference, unmasking from the front yields lower loss and is shown to be advantageous. To summarize the discussion so far, during training, MDM modeling is a hard problem than ARMs. Furthermore, after training, MDM exhibit imbalanced loss across the masking problems. However, most existing MDMs, despite training for the worst, make no attempt to plan or select favorable sampling path. To address this, the authors propose adaptive MDM inference, in which mask tokens are not selected uniformly at random as in vanilla inference. They propose passing the current state through a function f and then sampling the mask tokens based on the output of this function. This selection function f is designed to bypass difficult masking infilling problems during inference. The authors propose two representative approaches, top K and top K probability margin. Both are confidence-based method. In the top K approach, the K positions with the highest confidence are excluded from remasking, while all others are masked again. In the top K probability margin approach, the K positions with the large difference between the highest and second highest predict token probabilities are excluded from remasking, with the rest masked again. The authors demonstrate that when applied to the LNO and AST dataset, the adaptive inference strategy leads to notable performance improvements. In the text modality as well, adaptive inference achieves lower perplexity and entropy, further reinforcing that effective token ordering and planning is an important new objective for MDMs. Even in puzzle-style tasks where MDMs traditionally excel, such as Sudoku and the zebra puzzle, incorporating token ordering further improves performance. Remarkably, the MDM with token ordering outperform an AR model fine-tuned specifically for the order in which the problem should be solved. Let me now conclude. In my view, token ordering is a crucial topic in MDM research. Furthermore, in LADA, token ordering has been shown to be applicable even as the model is scaled up. Specifically, LADA applied a method similar to top-K remasking and reported a substantial performance improvements as a result of incorporating the remasking step. Future research directions include identifying the optimal token ordering for various domains. For example, in text data, should the ordering be strictly left to right, or might alternative ordering prove superior? Similarly, for code and mathematics, what ordering yields the best performance? These questions extend to the broader challenge in MDMs of determining which token ordering to apply in a given domain and devising methods to optimize it. Thank you all for your attention throughout this long talk today. I hope this discussion has provided you with useful insights, and I look forward to continuing the conversation in the future work. Thank you.